So, welcome you all to the second lecture of this bioprocess engineering. As we have discussed in last lecture that the bioprocesses, and the instrument which is used for the bioprocesses, or we can say the biological processes at a commercial scale, is called as a bioreactor. So here in this particular the diagram which is drawn on the board, so this is, we can say, a kind of a bioreactor. As I have explained you in last lecture that bioreactor and the fermenter, so both are basically same. The terminologies, why the terminologies they are different? So the reason behind that is, whenever you are using the terminology fermenter, so it is necessarily deal with all the fermentation processes. And whenever we are using a terminology as a bioreactor, so it includes fermentation as well, and the non-fermentation processes which are catalyzed or which are again facilitated by the microorganisms. So bioreactor is a broad term. So that's why generally bioreactor is used as a terminology so that it will cover all the microbiological processes which are processed in a particular reactor, or you can say a container. So this container is called as a bioreactor. So bioreactor is a proper terminology for explaining this particular kind of the reactor. So talking towards specifications of this bioreactor, here you can see the design. So here the H indicates the total height of this particular reactor. So this is basically a circular vessel. This is a circular vessel. I think you might have seen this kind of a bioreactor at our lab. So this is, we can see we have a smaller scale 3-liter fermenter, which is a kind of an automated kind of a fermenter. And in addition to that, recently we have installed some 5 liters, or we can say 5 reactors of having capacity 10 liters each. And very soon we will be having that 100-liter reactor. So basically this is a circular body, generally made up of glass, or you can say SS, the stainless steel. And this circular body, so generally the height is, this is called as the H. H is the total height of the reactor. Then obviously we are putting a fermentation broth, the media, culture media in this. So the level of culture media, so generally you know that we are working in the flask level. So we are not filling the flask completely, right? Yes, we are keeping some empty headspace. So some headspace should also be, left in this particular reactor as well. So that headspace has been left, and whatever the level of the water or the level of the media is there, so this is called as a level. So L. So this height is called as L. The height from the bottom to the media level. So this liquid level is called as L. Then the diameter. Diameter is called as capital D. Diameter of the vessel. So these are what we can say the geometrical specifications. Let us see what is the arrangement. So here, obviously, generally working at a flask level, what we are doing, so as to fasten the growth of a culture, we are putting the flask in a shaking incubator. So thereby the flask is continuously shake. You might have observed in your routine practicals. So that is a flask level. That is okay with the flask level. But how we can give the more aeration and agitation at say 1000 liters. So it is not possible to keep this 1000-liter reactor in somehow another shaker and to rotate that. So it is not possible. So there is a provision of a stirrer. So the one vessel is there, and so there is a provision of a stirrer. So that stirrer is continuously mixing all these ingredients. See, whenever we are keeping the flask in the shaker, so what happens is, all ingredients, they are mixed, as well as we can say the aeration is provided, because there is a cotton plug in the flask level. If you remember, we are putting a cotton plug, and whenever we are mixing it, so more and more air it will be entering in this particular flask. So as it is there is a provision of a cotton we have made, so obviously that air is a filtered air, and so the oxygen is supplied to the culture. So in this way, the more growth or more pronounced growth can be observed in a flask kept at a shaking incubator. So similarly, talking to this reactor level, so we have made a provision of a stirrer, and this the stirrer is what we can say it is the joint by which it is passing to the reactors. This is called as stirrer shaft seal. Here we can label here. This is as an agitator or impeller. Okay, fine. So this is an agitator or an impeller. So this is what we can say the sterile air line. See, this is a closed container. So how the air is supplied? So there should be provision of a sterile air line. The sterile air should be provided to the reactor. And how the air is released? So it is released through minute pores. This is called as sparger. So a part of a reactor which is responsible for providing the aeration is called as sparger. So this is what we can say a porous material, and this is releasing the air in the form of bubbles. So sterile air is supplied in the form of bubbles. So aeration is provided, agitation is provided. This is called as agitation, agitator or impeller. So this is what we can say for the aeration. Now the other thing is, see, whenever we are mixing something in a circular manner, so it leads to formation of a vortex. You might have you can experiment this as well. Like if you are taking water in a bucket and if you are rotating using a single central shaft, so it leads to formation of a vortex. Right? So that vortex formation, it is not good for the proper mixing. So it should be avoided. The vortex formation, it should be avoided. So how to avoid vortex formation? So there is some provision of baffles. So there are some part of SS they are placed in this way so that it is creating a hurdles for the vortex formation. You can imagine if you are in the same example I am giving, you have a bucket of water filled with water, and you are rotating this using a central shaft. Okay, so if you are putting something, say for example some scale, the measuring scale if you are putting, okay, if you are putting it inside of the bucket, so it will not lead to vortex formation. Are you getting me or not? So this is what we can say. We have to avoid this vortex formation by using the baffles. So these are the baffles. As mentioned, this is a working level. Yes, here there is the inoculation pipe. See, whenever we are sterilizing the reactor, after that the inoculation it should be done. Inoculation, the media addition should be done. So there is a provision of inoculation pipe. So that is an aseptic inoculation pipe, because we don't need any contamination over there. So for that there is an aseptic inoculation pipe. So you can see the knob is there. So whenever it is not needed, the knob is closed. In addition to that, important point, yes, the sampling point. During the fermentation process, if you want to know whether the fermentation is going in the right direction or not, how you can know? So for that, there should be a provision of a sampling point. So this is a sampling point. Whenever it is needed, the knob it should be open, sample should be taken, it should be analyzed, the knob should be closed. Right? So this is what we can say the sampling point is. After that, the drain point, very very important. Don't look at useless, but it's not a useless one. Okay, drain point is very very essential. Imagine you have 1,000 liter of a, see, if you are working in a laboratory scale, so at the end of experiment what you are doing, you are taking out the fermentation broth from the flask. So it is at a smaller scale, it is quite easy. But if whenever you are working at in 1,000 liters, so is it okay? Like, is it easy to take out all the liquid from the 1,000 liter reactor? No, it is not easy. For that, the drain point is very very simple. So at the end of fermentation broth, at the end of fermentation, the fermentation broth can be taken by using this drain point. So drain valve is open. The complete fermentation broth is drained, and what we can say, this is how we can say the fermentation broth is collected. This is, we can say, an overview of, or we can say the basic design of bioreactor. I think all points we have covered. We have covered the aeration, the agitation. There is a sterile air line. Then the impellers. So there are what? This is the agitator shaft. This is what we can see impeller blades. Fine. And this is what we can see working level. So this is what we can say the basic design of a bioreactor. I hope you have understood this basic design of a reactor. One more point I want to add here is, see, generally, what are the ideal characteristics of a bioreactor. So generally, whatever the joints, as I said, the material it should be glass or SS. If you are using SS material, so then there should not be flange joints. There should be a welding, so that it will be a smooth surface. Because if the surface is not smooth, it will give an opportunity, or it will give you a place for the adherence of microorganisms. So what we have to do is we have to avoid the flange joints. So the surface should be smooth as much as possible. Then most of the systems, it should not need high power. Say for example, for rotation, even for maintenance, there should not be any much labor should not be needed for maintenance of the reactor. Most of the systems should be easy going or automatic. So there should be a provision of some sensors. Most of the times we are putting some sensors such as the pH sensor, or you can say even the temperature sensor. So the pH or temperature sensor should be provided for the easy monitoring of the process. Then as I said, the material should be as cheap as possible, because we are talking at a commercial scale. But at the same time, it should also follow the containment regulations. You will very soon understand what is meant the containment regulations. But basically, it is nothing but basically we are handling microorganisms. So there are some regulations of handling of the microorganisms. So the material should be, no doubt, it should be cheap, but it should follow all the material regulations so that the microorganisms should not escape from the container. So that should be considered in mind. Rest all, we can say, if you are talking about overall any fermentation, so the fermentation media it should be available throughout the year, this is what we can say. If you are considering just the basic design, so these points, I guess, they are sufficient. So with this, I think it is better to stop here, and next lecture we will see in the topic. Bye.